First, we're going to have an introduction to logarithms. I stayed up and wrote this last night. I got very inspired. Because logarithms and exponential functions are totally related. They're cousins. One is the inverse of the other, so they would have to be related. So the first and most important form of relationship is this. Here are our exponential functions, and here are their inverses. If you have the function 3 to the x, then the inverse function is going to be log base 3 to the x, and 3 is written down here beside the g, but down beside the g. 7 to the x, the inverse is log base 7 of x. For 10 to the x, it's a little bit different. This is just log x. The 10 that would normally go right here is understood. We don't actually write it most of the time. Almost all the time, but I'm sure there are some times when you do. And now here might be the most difficult to get used to. First, E is a number. It's about 2.7, but it really goes on forever. The decimal part goes on forever. Its inverse is the ln of x, the natural log of x. But what the ln of x really is log base e of x. But somebody decided, hey, I don't want to write log base e. Actually, what I heard was it was a group of scientists, and they said, look, we use these logarithms all the time. So let's have just ln, okay, the natural logarithm. And so we'll take log base e, we'll save our hands from writing a lot, and have log base e just be ln. Okay, now, this, I mean, we may have gone over this before. I teach this in so many classes, it's hard to remember where I've said it and where I haven't. This part is called the argument of the function. Where the x is the argument. Yes, when we were graphing with transformations, we talked about the argument. The argument is where horizontal motion is. Left and right. Okay, so that's the basic relationship. You can come up with any base. If you wrote f of x equals 2 to the x, then the inverse function would be log base 2, see, it's the same base, of x. And there's the x. Actually, no, because, no, that'll be explained later. But the 2 and the 2 show that they are inverse functions. Okay, now you have to imagine, I mean, it helps if you can imagine. We're down here on this level with the bases. And when we see an exponent, we say, oh, that's moved up. But when you're dealing with logarithms, you're really up here on this level, looking down at the bases. So it's a different experience, but the same math that governs exponents will govern logarithms, because logarithms are exponents. Hard to believe, but true. So here's what's happening. You remember these rules, I'm sure. You might not have memorized, but you do remember that we went over them in this class. You've gone over them in previous classes. These are the rules of logarithms. If you multiply exponents, if you multiply x to the 3 times x to the 2, just for instance, if the bases are the same, then you can write this with one base and add the exponent. So when you multiply like bases, you add the exponents. When you divide like bases, you subtract the exponents. When you have a base and you raise it to a power and you raise it to a power again, you multiply the exponents. And the zero power rule is that any number raised to the zero power is 1. And the power 1 rule is that any number raised to the 1 power is just the number itself. There are similar rules in logarithms, but they're from the perspective of the exponents. So the product rule for logarithms is that, now these are just for instance numbers. These numbers are not important in and of themselves. I just chose them. Log base 3 of 14 plus log base 3 of 2. This is addition. But when you add two logarithms that have the same base, what you do is you multiply the arguments. So these two logarithms added together are going to equal log base 3 of the arguments multiplied, 14 times 2, which is log base 3 of 28. Nothing special about those numbers. Okay, when you, okay, here's the quotient rule for exponents. When you have like bases, when you divide like bases, you subtract the exponents. Here, we have log base 17 of a fraction, 5 over 14. What that equals is log base 17 of 5 minus log base 17 of 14. So you take log base 17 of the top and divide and subtract log base 17 of the bottom. The equivalent of the power rule for logarithms, here x to the 2 and then raised to the 3 is x to the 2 times 3. Well, here we have it with the ln. The ln, the natural logarithm, is just a logarithm, has the same rules. The ln of x raised to the 3, you bring the 3 down in front. That will be 3 times the ln of x. We can also write this with what are considered normal logs. How about log base 5? Log base 5 of x to the 3rd equals 3 times log base 5 of x. You have to learn it, you have to memorize it, you have to get flashcards or whatever helps you memorize. All right, the equivalent of the zero power rule. Zero power is 1. Any number raised to the 0 power is 1. Well, let's take log base 9 this time. Again, it's not important. Log base 9 of 1 is 0. In fact, the ln of 1 is 0. Log to any base of 1 is 0. You can count on it. Name a log, any miscellaneous log. How about log base 384? Log base 384 of 1 is 0. Imagine. Okay. Now the power rule of 1, here it is. Log base 3 of 3 is 1. Log 10 is really log base 10. But again, we don't write it. Log base 10 of 10 is 1. The ln of E is 1 because the ln of E is really log base E of E. Since those two numbers are the same, the answer is going to be 1. Anytime you see the base and the argument being exactly the same, the answer is 1. We're going to go through the steps of finding the inverse of a function. Remember, let's find the inverse of 3x plus 5 first, just to help remind you of the steps. 3x plus 5. First, you change f of x to y. Then you switch the x's and y's. Then you solve for y. So subtract 5, subtract 5. That'll give us x minus 5 equals 3y. The 5 minus 5 zeros out. Then divide by 3, divide by 3, so that y equals x minus 5 over 3. And what this means is that the inverse function of f of x, which is written f inverse, ugly f, f inverse of x equals x minus 5 over 3. This has nothing to do with the exponents over here, except we're going to use the same 4 steps to find the inverse of f of x to the 5, f of x equals 5 to the x power. This is an exponential function. So step 1, we change f of x to y, so that we have y equals 5 to the x. Step 2, switch the x and the y. X equals 5 to the y power. Now step 3 is what took mathematicians, professional mathematicians at the major universities of Europe, hundreds of years in the Middle Ages and into the late Middle Ages and into the Renaissance. Remember your world history there. They just couldn't do it. They couldn't find out how to change, how to solve for y in this case. Nothing worked. And then the answer was found by accident, by someone who was working on something else. Anyway, here's step 3, where we solve for y. Y equals log base 5 of x. So the inverse function of f of x is log base 5 of x. That's what a logarithm is. We are going to spend the day going back and forth and back and forth, and I need to add another page right now so that I can scroll this up where you can see better. So it doesn't even matter what it looks like really, but there. Okay, there now. Here we go. We're going to spend the day today doing what I'm about to do right now. Log base 7 of 49 equals 2. This is a logarithmic function. But why? I mean, this is really true. That log base 7 of 49 equals 2. How do I know? Because, watch this. The base 7 raised to the 2 power equals 49. You can switch back and forth between exponential functions and logarithm functions and logarithm functions and exponential functions because this is always, always, always going to be true, and that's what this symbol means. It means it goes beyond equal to total equivalency. A log has a base down here, an argument up here, and it ends up that this is the exponent. The exponent of what? Log base 7 of 49 equals 2. 2 is the exponent of the basic exponential function 7 raised to the 2 power, here's the exponent, equals the argument. The base raised to the exponent equals the argument. Now this is the most important thing that you might need to learn in this part of the semester, is that you can switch these back and forth just by remembering where the words go. Okay, so you already know what it's like to see the base raised to an exponent equals, oh, how about just, let's not do that. How about this? How about something you know? You know this so well, you could do it in your sleep. 3 to the 2 equals 9. Everybody knows that. But you can change this to a logarithm by remembering where the words go. Log, base goes down here. Exponent goes out here. I found it's easier to remember those two. Well, what's left over goes here, and what's left over is the argument. So the base is 3, the base is holding up the exponent. This is going to be, or here, let's do this. Totally equivalent, all right? Log. The base goes down here. The exponent goes over here. That leaves that. That's going to go here, and we call this the argument. Arg, matey. All right, so we're going to spend the day doing this. This is just a review, a very brief review of what logarithms are. Now it's not a review of what you know before, because anything that's being reviewed here is the exponential part. You have studied this for 2 semesters, even if you don't remember it, you have. You studied it before you got to college algebra, and then you studied it when you got into college algebra. But you haven't studied what the matching logarithms are. This may be the first time for most of you. I would recommend reading over this over and over and over and over and over. And really, flashcards are so cheap. Go over to Walmart, go to Target, go to wherever, order them from Amazon. Make your own. But put this stuff on flashcards and look at it every day. Okay. Make your own. Write them with your hand. Okay. So we are now going to go to the homework. Right here. This is your homework for today. We're going to be converting back and forth, exponential functions to their equivalent logarithm function over and over and over again. If you're going to disappear, why don't you stay around for a few minutes? Stay around for a few minutes until you get the hang of it. And then there's this one, and you really need for me to go over this one. I took the time to read the question help on this, and their way of doing it is stupid. I hate to say that. No, I don't. No, they go to so much more trouble to show you how to do this than you need. So I'm going to do this, but not now. No, we're going to be playing with these first. And once you get the hang of it, all it is changing where words go. Okay, kind of like Scrabble, except you're dealing with whole words, or a puzzle, a jigsaw puzzle. Okay, much the same. And I mean, a jigsaw puzzle with 3 pieces, you know, you can get that pretty fast. So that's what this is going to be. So up here, I wrote everything out the first time. We're being asked to convert this to that. And you can, okay, this to that. So the best way to do this is to label, well, create from the very beginning. Let the base equal b, the exponent equal e, which probably is not a good idea considering you're going to have the letter e also. And the argument be a, but hey, I'm stuck with it. Those are the letters I used. And so you need to remember here that an exponential function is going to be b to the e equals a. And I was thinking, how can you remember that? Well, you know, females are raised with this by well-meaning parents. Be an angel. Be an angel. How do you do that? Well, you got to be dead, right? Well, not good theology, but, you know, Anyway, the grown-ups always want you to be an angel. All right, B-E, an angel. I hated it when they'd say things like that. It just made me meaner. Which is a good way to remember it. When you really hate something, you can remember it really well. So, base to the raised to the exponent. Base raised to the exponent equals the argument. And then over here on the logarithm side, log, base down there, argument here, exponent over there. Okay, so that's what I did. I wrote this out first. Log B A, I don't know. You remember it. I leave it up to you. But okay, so log B A E. Well, the base is 8. The exponent is 1/3. And the argument, or the thing left over, is 2. And that's true. Now, I have a bone to pick with this book, with all math books, and it's because of the publishers. They want to save ink, and they don't put there should be parentheses around the argument. In the Garden of Eden, that's what God said, along with everything else. Oh, and on Mount Sinai, right, given the rules, the one that was left out was always put parentheses around your arguments. That's why the world went to hell. I hope someone's laughing. Okay. I may be in trouble for that. All right, log. This is the base, this is the argument, this is the exponent. Now we're supposed to translate this to base, exponent, equals argument. Okay, that means the 3 is going to go here. The exponent is going to go here. The argument is going to go here. See, this is not really difficult. In fact, it's just a puzzle. 3 to the 5 equals 243. Yep. Okay, we're going to do some more. The base is 10. Well, first, they want us to take this and change it to log base argument exponent. So the base is what holds up the exponent. The base is 10. Log base 10. You immediately know, or should know, because I'm telling you, anytime you've got log base 10, that's called the common logarithm. Log base 10. And then here's the way I do it really, okay? I mean, I remember where the exponent goes. It goes over here. So here's the base and here's the argument. I mean, no, the exponent. Here's the base, here's the exponent, 10 to the 3. Now the argument goes over here, and admittedly, yeah, there's not a whole lot of room for it. So log base 10 of 1000 equals 3. Or, since log base 10 is most commonly just written as log 1000 equals 3. And if you were to put that in your calculator, you would put in log 1000, that is, yeah, you would push the log button, 1000, enter, and the answer you'd get would be 3. Let's see what they do. Yeah, they write log base 10, but I'm sure they'd let you get log 1000 equals 3. That looks like I meant for it to be negative. I didn't. So let me. Okay, this looks absolutely horrible, but they want us to go from base to exponent equals argument. They want us to go from here to here, log base argument exponent. So B is 1024. Exponent, or E, oh, oops, is 1/5. And the argument is 4. So now I just fill it in. Log 1024, log base 1024 of 4 equals 1/5. And there it is right there. Log base 1024 of 4 equals 1/5. That 1024 needs to be smaller and lower. Okay, I'm sure it's a matter of printing, but it needs to be smaller and lower. All right, we've got e to the 2 equals t. We have a b to an e equals a, and we need to translate it to log base exponent argument. That's really the way I do it. So e to the 2 equals t. That's going to be log base e. A is t, okay, so of t equals e, 2. But how come that doesn't say that? Because ln is log base e. And we don't write that. We do write that. The natural log of t equals 2, which means that e squared equals t. It's just a matter of remembering where b and a and e go. Okay, e to the 1. B is the number e. E is 1. A is 2.7183. So we're going to turn this into log base e equals 1 of 2.7183. Well, except that it's ln, of course, because log base e is ln. the natural log. N stands for natural, L stands for log. This is what it's all about. This is called using the definition of a logarithm, and we are going to use it the day before the last day of new material to solve logarithmic equations. This is one of the methods. Okay, so that looks pretty nasty down here. But no, let's go back here. We're just going to do them all. We can do them real fast. Look at that, there's only one more page. What the heck? Are we lazy? Never. All right, now, B equals R, E equals K, A equals 144. We're supposed to change this to a logarithm. So this is going to be log. Should I put the formula? Yeah, B, A, E. So log base R of 144 equals K. And there we are. Now we're going to change from a logarithm to a logarithmic function to an exponential function or equation. I guess it is an equation. All right, so that's our base. This is our argument. And this is our exponent. So we're going to change this to B, E, A. Be an angel. Bleh. Okay, 5 to the 3 equals 125. And that's true. 5 times 5 times 5 is 125. Now, oh no, there's not a base. There is a base. It's 10. Don't worry. It's understood. Nonetheless, it is there. The base is 10. The argument is 0.001. And the exponent is -3. Group it all together there. So here's what we're going to write. B to the E equals A, which is 10 to the -3 equals 0.001. And if you put that in your calculator, that's what you'd get. Ln, oh no! Okay, I'm going to rewrite it first. Log base E, that's what Ln is, log base E, of 4 equals 1.3863. So now, your base is E, your argument is 4. Let's write this. Base. Argument. Exponent. Now then, no problem. We need to change this to be an angel. Which admittedly was just my way to remember it, but maybe it'll help you. Okay, so, yeah. All right, so I need to change E to XP, yeah, EXP, so that I don't get it mixed up with the real E. Oh, the number E. This is going to be E raised to the 1.3863 equals 4. And you'll have to put that in your calculator and see if it's true. Okay. Now number 11. Log base P of V equals negative C. That's B. This is A. And this is E. I'm sure you're getting the hang of this. They want us to change this to an exponential equation, and that has the form B to the E equals A. So, we're going to do it. P raised to the negative Z power equals V. Ta-da! And finally, this one. They were rude enough to actually write that on the other side when we're used to seeing it over here. So I'm going to change it. I have that power. Log base N of V to the third power equals X. Now everything is normal again. This is the argument. Oh yeah, I have to mark them. This is B. This is A. And this is E. So, B to the E equals A. There. It's all very mechanical. You know, once you get it, it's just moving letters. Just moving 3 words, base, argument, and exponent. It becomes very, very easy. Now, before we do this last one, do you want to discuss this? For some of you, it's totally new. No. Okay. Fine. I just remember that when I was a student and I was learning this, it was like, no way, nah, you gotta be kidding me. Although I didn't say kidding, I said something a little worse. Yeah. Okay. Well, we have some things that we have to learn. Like, what is the domain of the logarithm function? Because that's going to come into this. The domain of the log function. I should say logarithm, I guess, because it means ln also. Okay, it's this. The argument must be strictly greater than 0. It cannot even equal 0. All right, so what does that mean for this function? Here's the argument right here. The arg. Well, 3x plus 16 has got to be strictly greater than 0. Now I can solve this. You know, you can solve inequalities 99% of the time. They're just like solving equations. And this will be because we have a positive number in front of the x. We're not going to have to worry about reversing signs or anything else. So I'm just going to subtract 16 from both sides. That will zero out the 16 over here, leaving me with 3x. Bring down the greater than sign. 0 minus 16 is negative 16. So we'll have 3x is strictly greater than negative 16. Divide by 3. Divide by 3. X has got to be greater than negative 16 over 3. Well, let's get an approximation of that, shall we? I mean, I don't go around thinking in improper fractions. That actually is a graph of that. There it is. Yeah, I was working this last night. Negative 16 thirds is negative 5. It's actually, it exactly equals negative 5 and 1/3. Okay. All right, now that we know that, x is going to have to be greater than negative 5 and 1/3. This is what you want to think, negative 5 1/3. Because negative 5 and 1/3, if you look on the x-axis, here's 0, negative 1, negative 2, negative 3, negative 4, negative 5. Here's negative 5. And here's negative 6. This point right here is about negative 5 and 1/3. At least I'm saying it is. Negative 5 and 1/3. And to keep the book happy, we'll say negative 16 thirds. Okay, now it's got to be strictly greater than that. It can't equal that. It's got to be greater to the right of. So if we were going to graph the domain of the function would cover or go along with this part of the x-axis. Trying to make that a little thicker. I could just spend all day coloring. But there we are. This part over here will not have a graph on it at all. That's what this says. So the domain, for those of us who think in interval notation, it's going to go from -16/3 on the left all to the right forever. Right there. This is the domain of this function. Notice the base 3 doesn't have anything to do with it. Okay. Now, we're going to get a picture of this. Which, oh, wrong button. Which I also did last night. Here's the log. Now I used this, and we are going to talk about this. I used this last night, which is log base, which is math, and we go all the way down to A, log base, if you want to get that, where there's a place for you to put the base. It's not necessary. I'm going to show you how to graph it if you don't have that. Okay, it's just for us lazy people. It makes graphing easier. This is a graph of the function. Now here is, let me put a picture on here. I don't know why I didn't think of it last night, because it was already getting late. Okay, get smaller. I'm going to cover that up. There. Okay. Now I'm going to insert another page so I can lift it up more. Way to foresee that. If any of you are going to be teachers. Because you just don't want to sit and read your notes to students. I mean, that puts me to sleep. It also makes me not respect the teacher a lot. I mean, if they really got to read their notes, don't they know it? I can be too judgmental. All right, well, look at that. It bled through anyway. Isn't that cute? Well, forget that for a minute. And let's look at this graph. This is -5 1/3. Okay, and what we have going on here is a vertical asymptote. Okay, so let's draw that vertical asymptote. Logarithms have vertical asymptotes. Unfortunately, our graphing calculator can't draw them. A few people can make their graphing calculator show them the vertical asymptotes. I am not one of those people, even though I have my calculator marked to show me. It's supposed to show me the asymptote, and it doesn't. I've never had a TI that will show me the asymptotes, except the TI-83. Now that's a good reason to go back to the TI-83. But anyway, I'm not going into that. That is what 5 1/3 is. Now, what we're trying to find, let's get back to the problem now. This is what the graph, this is what this looks like. That's the whole graph. So this would be the graph of f of x equals log base 3 of 3x plus 16. What we have here is an inequality. What this is saying in particular, what this is saying is we're only interested in the part of the function that is below the x-axis. Below the x-axis. What the 0 means is this. The 0 means less than the line. Lying to you. Oh, yeah, no, I'm not. I'm not lying to you. Less than the line y equals 0. The line y equals 0 is the x-axis. They are the same. So we're looking for the part of this inequality that is below the line y equals 0, which is the x-axis. So moving. Okay, well, I can see where that is. If I can graph it, I can see it. And I am going to show you how to graph it without using log base, but give me a minute here. The part of the graph that is distinctly below the x-axis, so that'll be an open circle there, is this part. All I have to do is find out for sure what that is. It looks like -5. It probably is -5, but if it's -5.1, then I get a wrong answer. Yeah. So, but if that's -5, then I can say that the answer, oh, well, yeah, okay, I included the answers. The solution is, but we're going to find it. The solution to this particular problem is this. From this line, but not including the actual -5 1/3, because over here we saw, yeah, this has to be to the right of -5 1/3. Can't be on it. Okay, so for this little part of the x-axis right here, that is where the graph will drop below the x-axis. So the answer will be, to our eyes, -5 1/3. But not equaling, so no bracket. All the way to -5, where there's an x-intercept. But since this says strictly below, it's not going to be on -5. We cannot include -5, so the answer is going to be just in parentheses. And these are not brackets, they're not squared off. These are just extended parentheses. But what you have to know is, well, how the heck do I find out if that's really -5? We're going to do that right now. Okay. So log base 3. Now here is where the instructions in question helps go to so much extra trouble. So we're going to ungo to so much trouble. Log base 3 of 3x plus 16. I need to find where this crosses the x-axis. Where this crosses the x-axis is at log base 3 of 3x plus 16 equals 0. Now less than 0 means below the x-axis here. Let's a reminder, less than 0 means below x-axis. Greater than 0 means above x-axis. And equals 0 means on the x-axis. And if you're wondering, well, why do we care about the x-axis? The answer to that is the x-axis is, that is, what can I say? Values on the x-axis, numbers on the x-axis. Ah, I have it. Okay, it takes a while to put words together sometimes. We use numbers on the x-axis to say where the graph is doing something. Okay, so that's why. That's why we care about the x-axis so much. All right, now I'm going to part company with the question helps here, because we have just spent all of this time learning how to change from exponential to logarithmic functions and from logarithmic functions to exponential functions, or at least I should say equations. We're going to do that now. Here's the base. Here's the argument, the arg. And here's the exponent. Can you have a 0 exponent? Of course you can. All right, now I can get x out of this logarithm trap if I change this to the equivalent exponential function. In other words, base to the exponent equals the argument. How about that? Well, any number raised to 0 power. So this is 1 equals 3x plus 16. I'm going to solve for x. That'll tell me where this crosses the x-axis. Negative 16, negative 16. One minus 16 is negative 15. Divide by 3, divide by 3. X is going to equal negative 5. Yes! Woo! Okay. That number is negative 5. So now you know that this, for that little space right in there, that is where the graph is below the x-axis. And so by all means, write this way. Don't say 5 1/3. This is what you think, because it makes more sense. You can use that information, but this is what you write. And that, ladies and gentlemen, is our work today, which puts you out, ooh, 5 plus 3 is 8. 8 minutes early. 7 minutes early. But if you hurry, you can use all 7 minutes to do something fun, like go to the bathroom. Stay around if you have questions. I'm sure you will. This is all like Greek. Only it's not. But nobody knows for sure. If you go look this up on Wikipedia or wherever, if you look up the word logarithm, you'll see nobody is really sure how the word logarithm was chosen. There are different theories that are really interesting, but nobody is sure. Nobody is sure. It's one of those things. It's just like, why do Americans use M for slope? We are the only people who do. Everybody else in the world uses A. But we use M because we're different. Enough said about that. I look forward to seeing you. Oh, I'm not going to see you next Monday, am I? Technically, I am going to see you next Monday, but really, I know you won't be here because of Thanksgiving break. So I will be here, yes. If you have any questions, come on by, but we are not going to talk about anything new. So I'll just be the answer lady sitting here. Maybe I'll be doing my knitting. Whatever. Have a very happy and safe Thanksgiving. Please don't give COVID-19 to your grandma, please. Or your grandpa, or any of your sick relatives if you go to see your relatives. Remember, whether you want to wear a mask or not, their life depends on it. And that's my statement for the day. I plan to eat turkey and dressing and all of it. I'm going over to my brother's house, and he and his wife are going to feed me silly, and I'm going to take them cheesecake, and I will force myself to eat some. All right. See you November 30th. Monday, November 30th. But I will be here next Monday to answer questions. Bye-bye.